you remember the abstract, there was a third part about the porous media equation, stochastic porous media. I already embedded this in the first part. So then this afternoon I will lecture about the last part, which is the extinction for singular stochastic porous media equation. And this is more in the style of the talks and lectures, but I thought maybe at the end I should tell a little bit about current research or very recent research, because the other thing is basically everything is about well-known things, the general theory. So this will, the last talk will be more like a talk, like a lecture. But nevertheless, you can find the file. So download the file. So this lecture, which I already started yesterday, is just our attempt to extend the framework to cover more equations. Of course, the standard equation that I'm going to talk about, so that is Navier-Stokes equation, Perturbation equation, is all well known. I mean, that of course done in the literature many years ago. For instance, Perturbation equation by Jones, and of course other people. And Navier-Stokes equation, stochastic Navier-Stokes equation has been done. I think one of the first was Fleming, one of the two, I forgot already, in the 80s. So this is not new, and there's many papers after that. But so what we do here is just put it in the framework of the sort of monotonicity approach by localizing the conditions. So that is the main point of what we have done in these papers. Of course, then it's tempting also to look for new examples which have not been done before. We also have some of them which are presently being studied, so like surface growth models and so on. And at the very end, I will also talk about that. And also about this modified Navier-Stokes equation, the taped Navier-Stokes equation in 3 dimensions. And, so this would be another example. Okay, so I started this and I just want to repeat. So we are again in our situation. So we have a Gelfand triple. So this is first in the abstract framework. And so we want to solve this kind of stochastic equation with an operator A and a diffusion coefficient B, exactly as yesterday. And so these were the classical monotonicity conditions that I introduced yesterday. And then now we have the following modification. So just to recall, I did this also yesterday. So the blue color doesn't show very well. So the change is that in conditions H2 and H4. That's before it was like this. Now I change it. So there's a function which can depend on one of the two variables here, the V1 or V2. So let's say it depends on V2, which I can add here. So it's a locally bounded function on V. Coercivity has not changed, and the growth I allow also products of alpha and beta here. So this kind of thing. This is quite important. Looks a bit artificial, but it's really quite important to generalize the growth condition in this way, as we will see in examples. Okay, then we have the usual notion of solution of these equations, exactly as before. Oops. So it's exactly the same notion as before. And so now here's the main result. It's the abstract results. I will not give the proof. As I said, it's a modification of the existence and uniqueness proof in the case of classical monotonicity conditions. So now H1 and H4 refer to the new ones, and so the function f appearing on the right hand side of the coercivity condition. I need it's just technical. I mean, it has to be in LP half, and P must be bigger than beta plus 2. So what was beta? Beta was exactly this exponent here. So this can be quite large exponent, this beta. So as long as in the norm of the middle space, not the big norm, so that was the norm of the small space with the big norm, that should be alpha, so the same alpha is here, but this can be very big. And so the theorem then says, so if P is bigger than beta plus 2, this beta from the growth condition, and we need this kind of growth condition for the B, and the rho also should satisfy such a growth condition, so that is similar to what you saw in condition H4. These are just so conditions you need in the proof, and then if X is an initial condition is an LP, there is a solution also So the soup, so there is a solution which is unique, and this solution satisfies this. So this is not a condition for uniqueness. It's always unique, but in addition it has this kind of property. Okay, so I will not give the proof, but rather tell you about examples. Okay, so just some notation. So there is lambda is now always an open set with a smooth in RD with a smooth boundary. Partial derivatives are denoted by capital D sub I, and then we have the standard Sobolev spaces, and now I changed notation. So now before I was talking about H1P, so sorry, just to be consistent with the paper here, we use this notation W1P, where 1 refers to differentiation and P to integrability. And I think sometimes this is interchanged, but we use this order. And then this is the usual norm. So I take away the Sobolev norm without the LP norm, so just the LP norm with the gradient. We are on a bounded domain, so it's an equivalent norm. And for simplicity, we only consider examples with where the coefficients are time independent. I did this also in the first part of the lectures, but one can easily, of course, adapt all these examples to the time dependent case. So it's just twice, I'm sorry. So let me start now with semi-linear stochastic equation. Just show you at least one proof how you check these conditions to convince you they are really the right conditions. Not the best probably, but really the right conditions to formulate. And now here's a situation. So we just take V, classical Sobolev space in L2 or the 1, H is in L2, and then we just take the dual space. So that's our Gelfand triplet. Now I look at an operator that we have seen before, namely the Laplacian, but now I add also a first order part where the function Fi so depends on u, so it's a non-linear operator. Generally. So one example for that, which is by the way not covered, but the example you can have in mind is of course Burger's equation, where this Fi is simply the identity. Okay, so just would be u du dui. And of course you would not have a sum, so it's one dimension for d equal to 1. So why is it not covered? Because we have this ridiculous condition. Lipschitz is okay, Burger's would be covered, but we have bounded. Okay. So I will tell you about Burger's later on. We can also do Burger's. The point was here that Ray asked me, so can you help me to get rid of the boundedness condition? And I said, well, I thought a little bit about, well, not immediately, so I cannot do it. And so we left it in the paper. And now I pose this as the problem that I mentioned yesterday. So the first we can prove we can also get our conditions when Fi is not bounded, gets a free copy of the Springer exponents. Now I know how to do it, so it's possible, but I want to make you look into the proofs, which I'm not going to present here, but which are in the notes. So if you find the proof and drop the boundedness, so then we have really a situation where the Burger's equation is covered and more general things. So I leave this as kind of a little competition. The first one who finds it sends me the solution by email. So I will send a copy. Okay, so now let us look at the two different situations. There's one situation where E is just 1 and 2, so everything depends on dimension here, as you will see, because Sobolev embeddings come in, or very nice interpolation inequalities, they all depend on dimension. So if D is less than 3, so then we have exactly this kind of local monotonicity condition that we would like to have, even here with a minus sign in addition, but here this is the term that, so there's room for perturbation, by the way. So then this term I really need, and you see we have u minus v as before, and this would be the rho. Okay? And remember the conditions on the row is always this type. And so we have to be careful that there can be a multiplication of these two norms, but this should be the alpha from the coercivity. And this is usually 2. So it should not be worse. Should not be worse than 2 what we find. It's very important. Yeah? So if there's a higher power, we are out. Like in this three-dimensional case, the power is too big, so we cannot cover this case. Nevertheless, I wrote it, and you can check the proof. The proof is also, at least it says, some hints. I mean, in the file, you can find it, but the 4 kills are seen. So in the three-dimensional case, we cannot do this. We can only Fi take Fi, but independent of U. We can only treat the linear case, but I dropped it from the file because it's not so interesting. So in 3 dimensions we are out with our arms, just to show you how these things come in. Okay, now I will concentrate on this, and I would like to show you how you can prove this, because that is exactly what you have to do to check this local monotonicity, because at the beginning you might have thought, well, this is very strange, why do you add this function just depending on one of the 2 variables, but that's exactly what you need to do in order to cover the new examples. And now we will see this exactly. Okay, so now let's look at the proof. How can we do this? I don't know, this always jumps twice. Okay, so now I take this difference. I just want to show the local monotonicity. And you see this, there is a Laplacian part inside. So if you look at the Laplacian part here, so you have Laplace u minus v, comma u minus v, v star v, and then you just integrate by parts, and you get exactly the gradient. I did this yesterday, so this gives me these negative parts. It's very simple situation. And then this is just the definition of the nonlinear part applied to u, applied to v, comma u minus v. Now I show you our stupid proof, because we use the boundedness of that part. We're lazy, but it's impossible to do it without. But I show you the proof. Now this is very simple. So this, what I've done here, you see, I've just added this term fi u div, and I've added it again. Otherwise, it's exactly the same what is written above, and then we do simply hurl. So it's very, very simple. So we take L2 norm of this, and then times L2 norm of this, times this guy, you have to multiply. And then there's this other term, so this di goes out, and then we just have here the difference of fi, so we get this term. So this is the... Okay, now next step, so just this I just copy, and you see this is nothing but the V norm, it's the gradients here, so you get and you sum up, so this is just the V norm, and now I use the boundedness here, just drop this, and put it in the constant K, and just do this. So that is the lazy proof with the bounded assumption of Fi. And then you have this part again, so, oops, sorry, yes, this part we just did, then you have this part again, there's again the V norm. And then here I used this Lipschitz, so you can estimate this up to a constant times u minus v squared, so you get the 4 norm here. Okay. All right, and then you use all the time Young's inequality. So all PDE theory is based on 2 tricks. One is integration by parts, and the other is Young inequality. And the Young inequality is always of this type, so u is equal to a to the power p divided by d. So? Less than. Sorry. This would be fantastic. Yeah. B to the 2 prime, and 2 prime is the base and this is one adjustment. So you do it in a topological way. And then what you usually do, you put an epsilon here and a 1 over epsilon here. Yeah, and then you put it here, and you put 1 over epsilon here. So what I'm trying to say, you can always take the product of the 2 and make one sum as small as you like, and amalgamate it into another one. So that's always the trick.
And for particular electron, where we did the inequality.
I know. But I don't see it. Yeah, sure. Okay. Right, so then what you do here is, simply you have a lot of negativity here, and now you use this Young inequality. You do the square, so with a small epsilon to make it less than this one, so there's still a bit of negativity left here. So from this term and this term I just copy here. So you see, right, so just copy because this is just written like this. So now it looks already quite nice. The only thing is we would like to rewrite this in terms of the L2 norm. Remember the local monotonicity, this gives us some very negative stuff, which I will comment about in a moment, but we don't really need it for our local monotonicity. That's the right one. In the H norm, we have the difference square. And then we can allow also some rho of V, and we would like again have the H norm square. So we have to estimate the L4 norm in the following way, and that's a very specific estimate, only true in 2 dimensions. So here are these interpolation inequalities that I use. And so this is the best possible inequality I know, and I learned this, or we learned that from a paper by Minaldi and Tharan. And this kind of inequality can be proved completely elementary. Just you have to know the main theorem of calculus. You don't have to know anything about interpolation or sublimation qualities. And I really recommend, I checked it last night, it was quite tired because of the jet lag, but I checked it to be absolutely sure it's correct. It's written the 2 there, so everything's correct, I checked it. And it's really a beautiful proof. It's only 5 lines or something, so you should be encouraged to look at this. So now this saves us, because now you see the 4 norm square, I have no square in my equation. There's sorry, it's not a 4 in the equation, I just have a square. So I get these differences. Now here u minus v, this without the square and this without the square. But this is just a v norm. So if you plug this in, you get exactly what we need. Okay? And you have, of course, the v norm here. Again, use Young inequality, you put it in the first part. So then you get really exactly the inequality we need. And you see here is my rho. So unfortunately these are on 2 different pages, so therefore you see, oops. It's always in the jump. Yeah. Okay, so now I apply to this, so I estimate this by u minus v in the gradient of this, yeah, and then the 2 norm of this to the power 1. So there's 1, because there's square, there's just 1. And then you can separate by Young inequality and put this in the first part. This part you put in the first part. Here you just take a square. There's a 1 there because there was a 2 there for the difference, and then you get exactly what we want. Okay, and you have just a square there. It's very important. Now in 3 dimensions, and there's also beautiful proof in Minali's for this interpolation inequality, again elementary, you have a worse inequality. Okay, so now if you do exactly the same thing, forget about this part. This is just a mismatch. So if you look at this, and now you do exactly the same exactly the same kind of substitution and use Young's inequality, then unfortunately you get a 4 there. And that kills us. So 3 dimension doesn't work. Just to show you how the dimension comes in. This all depends on this interpolation. Okay, then if you look at this kind of inequality and you look at this part, you see immediately we have already we get from this also the coercivity condition. Remember, this was this condition. You know, this condition. We only have to look at the diagonal. I ignore the b for the moment. Just do it for the a. Okay, now if there is no v, so v is 0, a of 0 is 0, then you have exactly this a u comma u here, right? You have minus u v squared, so there's our coercivity. Alpha is 2, but now v is 0, so this part is not there. Okay? So therefore we have automatically also from this inequality our coercivity. Okay, so now that because of this coercivity, because of this minus part, so it's, some people call it sometimes strictly or very strictly dissipative or whatever, we can then make a perturbation of this, and I will not give you the proof, but the point here is, I don't know, it's very difficult just to do 1 page, it jumps twice, you see. No. Okay, so we have here our operator that we have just studied, and then we do a perturbation with a g, yeah? And then we look at this equation. So we make a perturbation simply by a polynomially bounded function with some r, and we also need this kind of, well, of course, one-sided Lipschitz condition, kind of a local one-sided Lipschitz condition where the y is allowed to grow like s. And so we can do such kind of a perturbation, and B is Lipschitz here, so I ignore a little bit all the conditions on B. You can check yourself, so they're just the suitable conditions on B. And again, we have this ridiculous boundedness assumption, which now we can drop, and I hope you find the proof. And then we have the following 1 dimension. We can add something that grows in power 3. And this is one deficiency of the monotonicity approach, that you cannot mix very easily the nonlinearity. So you cannot take the Laplacian, for instance, plus some polynomial of very high power which is decreasing. Yeah? This is not possible. So it is possible eventually, but it's not possible right away from the conditions, also not for the local monotonicity conditions. So we always have these restrictions, so depending on dimension. As you will see, this can be 3 in 1 dimension, in 2 it's worse, and 3 is even worse. Yeah? And then also this kind of, this S here, this also depends on dimension, and it's, so what finally comes out is more like a matter of diligence and ingenuity to find this result with the perturbation. And so in 1 dimension you can take R equal to 3, and the the S equal to 2, so this S can be 2 and this can be 3, and then you can just do a simple, then the perturbation works, so there is a solution of the stochastic equation, and now P has to be 6 here. So this is just now playing around with that, just for fun. And then D equal to 3, we can only do 3 halves, and S equal to 2, that's the optimal by our techniques, and we have to start in at 6. As again, so it's the same as above. And then in 3 dimensions, we have to assume, as I said, that the FIs are independent of U, so the boundary function FI independent of U. And then we can do again this R, but we have to be even more restricted with the S. And then again we have a solution. And the proof is included in the files. Just to, for those of you who like to get used to these arguments, you can find them there. Okay, well, but I will not go into this. So I just I skip it. Just skip on. Okay, now let me give you the argument for Burger's equation that this local monotonicity is really fulfilled. Yeah. Okay, and there's a very important thing what I'm going to use, and this is already hint how to solve the general case, which is the proof I found yesterday. So now let's look just at the local monotonicity for Burger's. So Burger's is now, as I told you, D is 1 and FI is just the identity. So our operator that we just studied is just has this nonlinear part. Okay, so now you write down, again you do integration by parts, that gives you this term with minus sign, and now you just write down the second part for U minus B, comma U minus B, so you have to handle this part. Okay, so maybe here's one step missing I should tell you. If you are used to Burger's, of course there's no problem for you, but if you've seen it never before, so this is of course, so that the integral is the same as this, so that is a 1/2 here. Then there is a du square by dx minus dv square by dx. That's the same. You agree? As u minus v. Okay? Okay, but this you can write as du square. This is the same as d plus v times u minus v. So d of u minus v squared. U minus v squared is the same as that. So I rewrite it like this, d by dx. And then I integrate by parts. That's exactly what I do. And then you get to the next line.
So do you assume that zero boundary condition?
Right, I should have said that. Yeah, it's always zero boundary condition. That's very important now. You're absolutely right. Okay, so then I write this u, so you see, if you do then integration by parts, you have here u plus v minus u minus v, and here u plus v, you simply write minus v plus 2v. Yeah? Okay, and then you see the following, I mean, you just do the sum here, so you have u minus v times this, dx by duv, plus the 2v part times this. But the 2v part, the 2 cancels, so the 2v part appears here again. So what we have to check is that this part with this is 0, but that's trivial because you have the same, this is the same as, so there's u minus v square times d by dx u minus v, and this is the same as to the power 3 by dx times some constant which you have to work out. Now you take the integral of this, but now you can do the integral. So this is this part on the top, this part evaluated at the bottom because of direct boundary condition 0. Okay, so then this part comes out. And such a similar argument can be done in the general case, which we just overlooked before we published the paper. Okay, so now we are in this situation. Now we do the usual business. We keep this, and then you see, you simply separate everything by order. You take the square of this to the power 1/2. That gives you exactly the h1 norm here. And then you have the square of this and square of this, and then you separate it by a 4 norm. So just hold on, so completely simple. Okay, and then we look at the next step, and now I have again used the fact that we can estimate the 4 norm, remember, to the power 4 by the square of the L2 norm plus the times the square of the gradient unit. Yeah? So that is, I just plug this in because now there is we have to take the 4th root, and then you just estimate this term correspondingly. So there's this term just to power 1 that adds, so we get a 3/2, and this I just leave unchanged. Okay. Okay, so then in the next step, as you can see, we end up here, and you've seen that before, this L4 to the power 4 doesn't harm us, yeah, because we can do this again by this trick of linearity, because of this inequality. Well, it's not maybe not due to them, but it's in their paper. You can estimate this by the gradient norm squared and then the B norm squared, and then this is just of the right power, so we have local monotonicity in the Porous case. Okay. And also you see here the coercivity, because again, if you take V equal to 0, then you have the diagonal estimate, and then you have here the minus, and of course if V is equal to 0, all this is 0. So we have Borges inside, everything is inside. Now what is more interesting, that also 2D Navier-Stokes is inside, so let's look at the 2D Navier-Stokes equation. Let me tell you a little bit about 2D Navier-Stokes. So this talk is a more relaxed talk. I tell you more about the models than about the really hard part of the proof. It's all hidden in the main theory. Yeah? You do it once and for all, and then the rest are simple checkings. Yeah? Okay. So now, this is the 2D Navier-Stokes equation, and I think if you talk about the SPDE in a general form like I do, one should mention this example. Yeah? The 3D case is open. Yeah? So just do the 2D, at least for global solution. Okay, let us start with the 2D case. So this is my space V. So you take all functions in the Sobolev space of order 1, 2, which take values in R2. So these are vector fields. It doesn't matter. So it's a nice Hilbert space, so we can use it. And with the property that the divergence of these functions is 0 in lambda. Yeah? So we can write down the divergence. So the divergence-free vector fields on an open bounded domain in R2 is smooth bounded. So with the corresponding node. Okay. So now we define H simply as the closure of V with respect to a 2 node. Okay. And then we can also, we can then also define it in a different way, but we chose this way because this was the most convenient. And then there is, if you now look at, so these are just the, now if you look at all vector fields on L2 vector fields on this space lambda, then you can project on those that have divergence 0, which are in this space H. So these can be thought of as the orthogonal projection under this, what is called the Helmholtz-Hodge-Leroy projection. I don't know, some people call it just Leroy projection if they come from France. If they come from Germany, they say Helmholtz projection. If they come from the States, they say Hodge projection. If they're all together, we call it Helmholtz-Hodge-Leroy projection. If you're somebody from the Fiji Insel, maybe he has another name to put there, but I don't know. Okay. They're all great mathematicians, no question, but I find it a bit ridiculous with all these names. Anyway, so there's this projection, so it projects onto the closed subspace of divergence-free vector fields defined here in the previous way. Okay, so and then we can define what is called the Stokes operator. So this is defined on the so on W22 intersected with this V into H. That means the divergence-free two vector fields. You can, by the way, if you prefer, you can also define this H to be this space, and all functions in here, where the distributional divergence is equal to 0. In the sense of Schwarz distributions, it's the same. Okay, now you define the Stokes operator, so in this space of divergence-free vector field, so that's just the Laplacian applied now to this vector value thing, just component-wise. Then you project it down, and then this constant, this comes from physics, the viscosity of the fluid. So whether it's very viscous or not so viscous, or viscous, not vicious. Okay, so now we can formulate the Navier-Stokes equation in the following way. So in a sort of abstract evolution equation form. So U prime now, that's the solution we are looking for. So that's the time derivative of the vector field is the AU, that's the Stokes operator. FU I will explain in a moment, and plus some external force F, so which we assume to be an L2 with values in the big space. And then F now is a function on a certain domain. We will see it can always be extended to V cross V. So it's a bilinear function initially defined on some subspace, maybe of smooth vector fields, which are just in L2 plus divergence free. And in W1 plus divergence free, and is defined as follows, FUV. So you just take U, so that's the guy that we do not differentiate, coming from the L2 space divergence free, times gradient, and this is the guy we differentiate, so it should have a derivative. Okay, so this is well defined, and then I take the projection because this is a vector, okay, this is a vector, the whole thing is again a vector, so then if you project it so this might not have divergence 0, even if U and V have. So then we project down to make it have divergence zero by force. Yeah? And then we have this operator. And then it goes again into L2 with the condition that divergence is zero for these vector fields. And then just the normal notation on the diagonal, you just call it f of u. Okay, now we look at the standard Gelfand triple. So remember, this is L2 plus divergence 3. This is W1, and that's the plus divergence 3, and that's the dual space. So then it is easy to see that all these mappings, so for the Laplacian I told you, then this can be always extended from here to here, and the same is true for the Stokes operator. You can extend it from here to here. And for this nonlinear part, also sometimes called the hydrodynamic part, this F, it extends to all of, not extend, you restrict it here, so that it's defined here. So it shouldn't say extend, but just restriction. This is an extension, that's not a restriction. Okay, so, but if you think of smooth vector fields, it's an extension in any case. Now we have very important properties because of divergence 3, and this I leave as an exercise. So this is sort of a thing which probably everybody has already seen. So if you take f u v, you put it in the inner product, the dualization between v and v star, and this is the same v, then this is always zero. So let's try to remember this because I'm going to use this all the time. So f u v, comma v is zero. So if these two guys are the same, the last two are the same, zero. And then more or less for the same reason, namely because we have divergence-free vector fields, you can always interchange these two guys if you put them in the dualization. These two guys you interchange, you see, just interchange, and you have to put a minus on. This also comes from the divergence field, so it's quite easy to change. Okay, so now we look at stochastic version of the Navier-Stokes equation. So that is the Navier-Stokes equation I wrote down before. What I did not do, because I sort of assume that you have seen Navier-Stokes before. So if you look at the derivation for this equation, it's just describes the velocity of a fluid going to this lambda. And then if you look at the particle-wise and you want to write down, what this is, then this hydrodynamic term appears naturally. If you have not seen it, I can explain to you in your brain. But I have not put this in the file. So this is a very famous equation. Okay, so now we add a stochastic, so this is an external force, and then we add a stochastic term, which can also be thought of as a stochastic force. And I want to make one remark about that, because many people say, well, we look at SPDE forced by a stochastic term, and really this is not correct. Physically it cannot be a force, because here you have only the first derivative in time, not the second. If you think of Newton's law, it should be the second if it should be the force on the right hand side. So that's really wrong formally. You cannot call it a force. Now in this case, this is first remark. Second remark, for the Navier-Stokes is more justified because this is a velocity. So then we have a derivative, which is acceleration, that's fine. But they do it in general for all stochastic equation, even if it's just a position on the left-hand side, the xt, they always call it a force. And what is behind it is what is called the famous Kramer-Smoluchowski approximation. So if you write it in Newton form, so with the second derivative, you can always do that. Then, and you put an epsilon in front of the noise, and you put an epsilon, if you like, in front of the mass, and you let the mass go to zero, then it converges always to an equation that we are used to. So in the sense of Kramer-Smoluchowski approximation is really true to talk about a stochastic force, even if you have the position vector on the left-hand side, having always this Kramer-Smoluchowski approximation in mind. There's a beautiful paper by Mark Friedlin not so many years ago, where they have done this just in one dimension, and then there are papers also in infinite dimension by Sandra Cherai. So if you're interested in this kind of Kramer-Smoluchowski approximation, there's quite a lot of work about it. Okay, but now here is more justified because I said this inside the velocity, that's okay. Okay, so now this is the assumption on the noise. So it's kind of Lipschitz, and again it's kind of local Lipschitz. So we can also allow here this Fobismus. Of course, nevertheless, this will have linear growth because you just put this equal to zero, then this part is not there, and you see you really get a linear growth in the no, it's not bigger than linear growth, because you put this equal to zero to show the linear growth. Okay, anyway, so then 3,9 is a unique solution by our general result. Again, we always apply the general result, and we have to take p equal to 4 here, which is not so surprising if you see the 4 there. Now let us check the local monotonicity. First I start with the coercivity, H3. So you have to write the operator on the left-hand side, the map, comma V. Now this A is just a part. Before this, all this was A, non-linear operator. Now the AV, this is a Stokes operator. Don't get confused. Yeah? So the whole A from the general framework is this little guy. Okay, so the first one is just again integrating by parts. You get this because you have AV, comma V. You can integrate by parts. So you get this part with a minus sign because I integrate, you get a minus sign. Sorry. And then there's FV, comma V, so you see for the coercivity, and that's the main point, it does not contribute because FV, comma V, remember, is 0. So that's not there. So therefore, there is coercivity. And then this you just estimate like this. And then again, you use this Young inequality for P equal to 2, and then you can put this guy into that, so you get a little bit smaller constant here with the negative sign times the constant times this. And you see that's exactly the coercivity that we need. So that's very simple. And then for the BV is linear growth, I've written down here the inequality, so that doesn't then harm our, because just the H norm term that adds on the, if you take the sum of the two that adds on the right, so definitely we have our coercivity condition. Now let us check the local monotonicity to convince you that it's really the right thing to do. Yeah, for experts in Navier-Stokes, this is immediately clear once I write down those conditions, but maybe not all of you have seen that, so I just give the argument. So first of all, here's a mistake. There should be square there. So if you just make a note about this, because by homogeneity this cannot be true because this is a quadratic form in W. It's not a positive definite, but it's a quadratic form in W, so there should be square. Okay, this is correct. Okay. So let us just concentrate on the second one. The other one is just used to prove H4, and I will not prove H4. So in order to prove the local monotonicity, this is enough, just to have this. And now we sort of recognize the three-dimensional inequality I wrote down before from the paper by Menalis as Natam. And then you get exactly this kind of inequality. Yeah? So this is followed directly from, maybe I go back to convince you. Sorry about that. It's exactly this guy from the Menalis-Differential. Okay, so if you use this, then you get this kind of inequalities. It's again a little exercise. Sorry. Okay, so this is the inequality I'm going to use. Okay, now we start for the monotonicity. And first do the F part, the nonlinear part, big F, capital F. The other one doesn't depend on you. This drops out, so it's only the capital F and the A part. So later on I will just add them. Okay, let's do the F part. Now if you look at this, then you see immediately that only the cross terms survive, because if you have FU, U, the last two guys are the same, 0. If FV, V, last two are 0. So what you just get is FUV and FVU. Okay? And then what I've done here, so I've just added 0. So here's the F. Where is it? So here's the FUU guy, V, which comes from here, and I subtract FUVV, but again the last guys are the same, so that's 0. I've just subtracted or added 0 here, and the same, this guy is 0. So only this guy was there from here, FVUV, and I have FVVV, so 0. I just added 0. No, subtracted 0. Okay, but now by bilinearity, remember this is linear in U and V, so I can put these together. This is the same, this is the same, this is the same, this is. So it's trilinear, all the others are the same, I can just put them together. So I get this. So this is first algebraic computation. Algebraic computation is the trivial part. So now comes analysis. So we have now, again by what I just told you. So now I use this kind of equation. So here you see V and W are different. So I can actually apply now this. Now I plug this in. Everybody can check and just plug this in and I end up here. Just by plugging in this. And then again, Young comes in. Yeah? So then I just order. You see what I've done? I just separate them to get a square here. So I have to take whatever 4/3 up to the power 4/3. So in Young, it's 4 is with P4/3 and P prime 4. Yeah. So then you get this, and then the 4 here comes out, and here times 4 you get this. Okay, and then we're done. because now the A doesn't matter, it just adds a very nice part here and kills this part, because this is bad for our local monotonicity, but now we can kill it. And I've taken young with epsilon here, whatever, half or whatever, quarter, a nice small thing, so that there's a plus here, which is very bad, because for the monotonicity with this, but the A part gives a minus mu here, so the plus mu half then makes it a minus mu half. So still is fine. So the strong dissipativity coming from the Stokes operator saves us, and we get then just this is there, and now you can look at this, and then again use that this can be estimated by gradient U, L2 norm, U, L2 norm, you plug it in, and then you see both are just of just square, so that means we have really our conditions on row. Yeah? So conditions are fulfilled. So we can apply the theorem and we get existence and uniqueness on Navier-Stokes equation. By the way, in the growth condition, because I said this before, I just want to go back to the general conditions. I said before that it's very important that we allow here this beta. So if you check now in the Navier-Stokes case, the growth condition, you really find a beta here. Yeah? This term is really there. So the usual monotonicity doesn't count in this case, but now it's counted. So you now have to go again back, and then we have done the 2D Navier-Stokes. Okay, maybe the battery is a little low, so it doesn't it jumps in the top. Okay, so now I even weaken the local monotonicity conditions again, and so again the blue doesn't really show very well. So now the next step is it's weakened local monotonicity. What I've done here, I also allow a function that depends on the other of the two B1 and B2. Okay, so then we have now, let's call it eta, an additional function. So again, having the same properties. And sorry, the growth condition I just keep as before. And in the coercivity condition, before I had just a constant times VH square. Here we allow much larger growth here in the coercivity condition. So there is alpha bigger as before, alpha bigger than 1, some beta positive, and the delta. So this is the positive function here. So we really have coercivity, and then we weaken the condition in this way. Why do I do this? Because I would like to also cover 3D Navier-Stokes to get a result about local conditions. So this is a bit boring now in the sense because I don't give you much of the proofs, but just show you if we do this little twist, also the other thing is inside. It's just my aim is to motivate you to look into this machinery a little bit, so then everything is with one hand wiped out. Yeah? So we do many things in one go. But the main point of this part of the talk is to give you more examples, not just the 3D Navier-Stokes, but also the tame 3D Navier-Stokes, and then Cahn-Hilliard equation, and also the surface growth model. Yeah? So just to explain you that where these equations come from, and they're all now inside this framework. However, we pay some price for this kind of generalization, which I will tell you about in a moment. So G is just at the moment only a non-decreasing continuous function, and then again we go into the machinery and modify this here and there, and we can do first of all only the deterministic. So here's a big problem for us. We can do the stochastic, but only with additive noise, not with multiplicative noise. The Navier-Stokes we could do with multiplicative noise. Part of the community doing Navier-Stokes is multiplicative noise is not such a big problem. For others, they consider it a big problem. Yeah, but now, at least with our approach, we do multiplicative noise like this. But there's many papers where they say we cannot do multiplicative noise in one way or another. And so I just want to say this, there may be different opinions where there's really a problem to do multiplicative. I think it's not a problem. But now here really it's a problem. So with this approach we cannot do the multiplicative noise. But it's three-dimensional, not two. Okay, so let us just look at the abstract evolution equations of this type. There's a nonlinear operator defining all our conditions, and it's just a case where the B is 0 in the stochastic part. So we know these equations already. And here is just, because it's just, you can weaken a little bit the measurability conditions. I will not go into this if there's no stochastic part. If we have a stochastic part, you need to assume always this progressive measurability stuff. Okay, if it's the A also depends on omega. Okay, so that is just, I don't want to go into this. Now under this now, again weakened conditions, we have again an existence theorem, at least first of all for the deterministic case. Okay, so local solutions always exist. So given any initial condition, there exists a constant such that for one, which is this deterministic equation, for one has a solution up to this time t0. And we have this regularity of the solution, exactly what you would like to have. Yeah? So that's standard. There's nothing new here for the Navier-Stokes. What is new is this, but put it in a general form. Okay, and the derivative in the dual space. And then we have in this sense a solution. So for instance, written just in the weak form. So that is what Professor Krüger and Professor Jönsch have used all the time, that write the solution in weak form by just taking in a product with element in V. Sorry?
Can you relate this T0
Yes?
with the initial condition?
You can. Yeah, but we haven't written it down here, but for the 3D Navier-Stokes we get the usual condition that you find. I write it in the 3D case. Okay, so what we also have to assume that our two functions appearing on the right-hand side of the local monotonicity again have to have this growth as we have seen before, both of them. So we have existence in general, and under this additional condition that we have seen before, we have a unique solution up to this. Now, if in the coercivity condition, remember, coercivity condition, I allow this G to be anything. Yeah? But if it is really linear growing as before, then there is a global solution. That's exactly the difference between 2D and 3D. In the 3D case, this G is not linear growing. 2D is linear growing. So we have global solution. The 3D is not linear growing. It's growing faster, so we only have local solutions. Okay? So that's the result. Okay, so now let us go to the stochastic case. So now we just add an additive noise, and I have done something funny here. Before there was an A of txt dt. Now I do two parts, and there's a certain reason for that, and I will explain that. So now I think of A being given as a sum of two operators from 0t cross v to v star, and they're not depending on omega. We are just for simplicity, we don't do this. And then the bt is just also not random here. Yeah? But it's additive noise, but it can depend on time. Yeah? So this doesn't depend on the solution. Otherwise, we are exactly in the same situation before. W is a U-valued cylindrical Wiener process, and B is a Hilbert-Schmidt valued from U to H, so exactly as before. But it does not depend on the solution. Okay, stopping times we denote as usual by tau. So then we have the following notion of solutions. An H-valued FD adapted process is called local solution if we have this, P or Moshuli, and we have this equality. And it's also continuous here, should be continuous H-valued process, just the bottom. But it's only defined up to some stopping time. So that is just the usual notion of local solutions. So that's the definition. And now here's the result, again without proof. I just make a remark about it. So we need, and that's another catch, we need that V is compactly embedded into H. We try to get rid of this condition, we're not able to. It's another problem to you, but I don't know whether it's possible. In contrast to the other problem. And now let us assume, remember we have two parts in our equation. A1 satisfies the usual local monotonicity, not this weakened one. Okay? Let us assume this. So this is exactly rho is equal to 0. There's only eta. Eta was the former rho. And the beta is 0, and the G is linear. So that's a solution according to the previous section. Okay? So there is this A1 satisfies this equation. The A2 satisfies the new equation, the new conditions, the relaxed conditions. And then we need, okay, this is technical, rho has to be sub-additive up to constant, eta has to be sub-additive, and then the usual growth condition on the two. And then we have, there exists a unique local solution up to some stopping time. And again, if also in A2, in the coercivity condition, the G is linear growing, it's a global solution. If it's not linear growing, it's just a local solution. Yeah? So in a sense, this theorem, which proves, for instance, for 3D Navier-Stokes nothing new, but it is bookkeeping in some sense. Yeah? So what do you need for one? So it's more pedagogical than research for the 3D Navier-Stokes. Okay, so that's the result. So the proof again uses monotonicity, means mean t trig, and so on. All goes inside again. Yeah? But so it's not completely easy, as you can imagine, but it works. Okay, so now let me give you the idea of proof. So, apart from all this big stuff, the idea of proof is the main point is to subtract the noise to make it a deterministic equation. That's what you usually do. If you have an additive noise, like this one, you just write it in integral form and you subtract this guy from, so put it on the other side and you write down an equation for x minus integral of this. That's normally what you do. Yeah? The problem is only then we need conditions on B to make sure that x minus this integral is again in V. Remember A, only x on V. So we have to assume that this is Hilbert-Schmidt from U to V, which is bad. Yeah? For applications. So therefore, we do the following. We do not subtract the noise, but we subtract, forget about the A2, we subtract the solution of this equation with A2 equal to 0. Now if A1 is sufficiently coercive, which it is by assumption, there is a solution that takes values in V for almost all times, which is enough. So I do this usual shift trick, not only with respect to a good stochastic integral of B dWt, or maybe only for Einstein-Uhlenbeck. I do it for a reference process that satisfies the usual local monotonicity conditions. And that is the trick why it works in such generality. So this was what Wei found. So I found it very nice. So now you look at this equation. And so this is just the usual monotonicity. So we have just the coercivity with the linear growing G on the right hand side. Then you look at this difference. Okay, so now you would like to solve the equation where there's also A2, and you just write down the equation for the difference of x minus 1. And then you can do everything. So that's the trick. By the way, going to a reference process, which is not just subtract the stochastic integral or subtract some kind of an Einstein-Uhlenbeck, but do it for general processes. So at least in my group, the two young guys I have, many postdocs, but so it was found by Wei Yu and by my other student Benjamin Guess at the same time. But they're not quarreling about priority there, but it was just funny that they came to me and said, I have this wonderful idea, and then half an hour later the other one came, I have this wonderful idea. So I cannot say who was really first. Okay, so maybe it's already known that I asked several people, and at least for the processes here, nobody used this trick. Normally people just subtract the Einstein-Uhlenbeck. That's a known thing, but not other reference processes. And it can be very useful because Benjamin Guess used it to really solve the stochastic equation in the monotone framework, where you can add a polynomial of any order, but it should be decreasing. So that just follows. It was very well known in the deterministic case, but now also can be done in the stochastic case by this subtraction trick. Okay, so that is exactly what I'm saying here. And then the last thing is that if you think of what happens if you replace boundary motion, for instance, by Levy noise, this has already been done in this paper again by Wei Yu together with Zizak Brezhnev and his postdocs and his postdocs. Okay, so now I will not talk about the general result, but just explain a little bit about applications as I promised. Yeah.
Not the global, the more general one they didn't have with Brezhnev, right? It was just the local monotonicity.
This one?
Yeah, it was just local.
Well, they have just the local
But it can be done?
But it's exactly what's said here. Yeah? So
Okay.
it can be obtained from the main results, and the rest of the proof can be carried out as in this paper. Yeah, so that's good. But such statements I don't like very much, because somebody is then stopped to do it, yeah? Because we claimed it already. We haven't done the details, so everybody's invited to do the details. Okay, so now we go to the three-dimensional case. So it's exactly the same as before, the Navier-Stokes equation. Yeah, remember, the time derivative is nu times the Stokes operator. Laplace now stands for the Stokes operator. Now, so far we have not taken the Lee-Wright projection, so the pressure also appears. But then if you take the Lee-Wright projection of the whole thing, I should say Helmholtz projection, I'm German, so Helmholtz projection. So if you take the Helmholtz projection, then this will drop out. Okay, so then we go back to the same form of the Navier-Stokes equation as we have written it in 2 dimensions. So now here again about the background, now we have 3 dimensions, so really the physics come in. So we have so U represents the velocity of a fluid field, yeah? So it's 3 components. Nu is the viscosity constant, the pressure is an unknown scalar function, and that is known as kind of an external force acting on the fluid. And now here, Levi, as you see, is a very classical paper from 1934. He proved, for instance, the existence of weak solutions, even in the whole space, but nobody knows whether they're unique. And then local solutions, I mean, this is in books already. I mean, these are newer books, but also in older books. We have a strong solution up to some explosion time. So we prove nothing new. So it's just that we show it fits into our framework. And then I do exactly the same kind of construction as in the two-dimensional case. So now I show you another construction that leads to the same thing. So we start simply with the smooth vector fields. Now we have vector fields on R3. And then, so these are the standard Sobolev spaces. And now I use these equivalent norms using this operator because it's more convenient. And then I simply look at the classical Sobolev spaces and I just take those with divergence 0. So if n is equal to 0, so this is the number of derivatives, there's no derivative, then this is meant in the sense of distribution. So that is exactly what I mentioned before. Okay, so the main problem is to verify the growth condition H4, and as I know, coercivity condition is only fulfilled for G that grows faster than linear. Yeah, so this is the price we paid, so we only get local solutions. But nevertheless, it took us some time to find the right, to also satisfy this growth condition in the previous form. And the trick is to shift, well, many people do that, to shift the pivot space, so the intermediate space. So now we take as an intermediate space the space H1. Yeah. V is H2, it's just the space, H1, H2. And then we just take the dual space. So now we work with this intermediate space, not with L2. Of course, then the process will be on H1, and we can only start on H1, but okay, that's fine. And one important thing also to prove this H tilde 4 is this very well-known but very beautiful inequality in 3 dimensions, namely that the suit norm of a function can be estimated like this. So this is I do not know whether it's really due to Haywood, but normally this paper is always quoted for this. It's also in the book of Xia, this Chinese mathematician who worked in this area. So that is this kind of inequality, estimated by the L2 norm of the Laplace of U, yeah, and then the gradient U. And here, if I write 0 here, this of course we have also applied the Levi projection, and then here's this. Okay, that's the famous inequality that is to be used to verify H4, but I will not do this. I will just tell you the example, and then everybody is invited to check the conditions, and it's all written in the paper. Okay, so again we take our old projection, the Levi projection. I don't want to go into details. Then we can rewrite it like this. So the pressure drops out, and now we call this B. This is because it's from the different paper. We call it B before we call it F. I'm sorry about that. That was little f, but I hope this is no problem. But otherwise, it's exactly the same definition as you have seen before. So everything is well defined. And then here is what you asked about the explosion time. So F is now the external force is just given. Everything is deterministic. I haven't done the stochastic case yet. U0 is then there exists a constant T0 such that we have a solution in the space you would like. And you see this is the intermediate space, so it takes values in H1 as a continuous process. And so the initial condition of course is also in H1. And then you have an explosion time, and you see it can be calculated in terms of the initial condition in the usual way, and of course the external force. CC given constant. This depends on the viscosity. You can do even more careful analysis. Okay, so for simplicity, we only consider now the deterministic case, but then going to the theorem 5.2 with additive noise, we have the same result in the stochastic case. Okay, so now this is my baby, the tame 3D Navier-Stokes equation. So this was an idea of Xichen Zhang when he was my Humboldt scholar. So one day he came into my office and said, why don't we look at the modified case? And because he read in the paper of Lyons, and he said, no, we should study equations where the solutions are the same as the 3D Navier-Stokes equation if you can prove that it exists a solution. Yeah? And then by some argument, Lyons met in this paper said it should be bounded to the solution. Okay, so this is we just believe it. Okay, in the case of 3D Navier-Stokes, we can see that the generalized coercivity only holds with g of x not going linear, but even to the power 3. So you get on the right-hand side the h1 on to the power 6. So which is okay for local, but not for global solutions. Okay, so hence now what we are going to do, we are going to add a counter term, yeah, that takes care of this to the power x to the 3. So we add something that makes it coercive, so it just counteracts this g. And you see what we take is we take a function gn, which at least far out, so if this is very big, this is linear, so that means you get power 3 and then times u, sorry, power 2, and then times u, you get a power 3. You get minus to the power 3, and that kills exactly the other to the power 3, and it becomes globally coercive. Yeah? It's just a way to do this. Okay, so I will tell you the definition of Gn at the moment, but otherwise it's exactly as the classical Navier-Stokes. This part is the same, this part we have not taken the projection yet, this part and this part, and we just added this counter term. But now it is defined in such a way that if the original one without this term has a solution that is globally bounded, then this is bounded, then this is 0. Because it becomes 0 once this becomes bigger than n. Okay, so we study the solutions, we all said in that paper is correct. We study the same solution as the 3D Navier-Stokes if you can solve it and prove it bounded. The things that should be bounded. Okay, here's the function. So Gn is 0 if what you put in there is less than n, so you don't see it. So if the solution is less than n all the time, it's not there. So we look at the taint of the Stokes equation. So this term comes in now. Of course, we take the y projection, and here we might okay, and then we can apply our result, and it says so for any f and any u in H1, 6-3 has a unique solution. Good, yeah, because this gives us exactly the coercivity that is needed. Okay, now this equation also in the stochastic case now has some interest because it is related to the original equation, and so there has been some activities now to analyze this equation and also the stochastic one. So for instance we proved small time large deviations and several other things, and also small times of small noise large deviation and small time large deviations for that, for instance, but there are other things that have been done for that as well. Okay, so then this is this taint of Stokes equation. So now the next example is the famous Kahn-Hilliard equation. So you see it's written here, and you see that the linear part now is not just a second order operator but a fourth order operator. So the Kahn-Hilliard equation is a classical model to describe phase separation in a binary alloy and some other media. So that is, for instance, a very nice paper where you can understand the physics of the model, and also this one, and then the part of the Bush were one of the first to analyze it with the stochastic forcing, that we know, the stochastic term that I will add in a moment. Okay, so look, it has the following form. So this is the linear part, and these are the boundary conditions, and here's the non-linear part. So it's kind of a porous media. Remember, this was the main part in the porous media, and the porous media part. And phi, let's say, is a polynomial function. Can be done more general, but just let's do this. Okay? So now the pivot space is again L2, and V is just the space where Laplace, bi-Laplacian, whatever you want to call this, Laplace square is defined, and then we take the V star. Okay, and then these are the conditions. So phi is a polynomial function in the classical Kahn-Hilliard, but you can generalize a little bit. You can take any function C1, and with this kind of, so it should be, derivative should be bound below, should be polynomially bounded, and again should have this kind of local Lipschitz condition that we have seen before, maybe in a little bit different form. And this is the catch. Yeah? So this growth is only allowed to be as much as this guy, otherwise it doesn't work. So we need this kind of bound. So it means, for instance, for one dimension can be up to 5, yeah? And then for higher dimensions smaller. Anyway, so then by our result we can find there exists a unique global solution. So it's not just local, it is global. So we also come here and it's inside. And we have an analogous result to this if we take the Kahn-Hilliard equation perturbed by additive noise. So the last one is maybe more recent, and this is what is called the surface growth SPDEs, and they look as follows. So we consider a model which appears in the theory of growth of surfaces, which describes an amorphous material deposited in an initially flat surface in high vacuum. So here are papers, in particular this one, that gives you a bit about the physics, and then you see Dirk Blomka, Marco Rumito, and Franco Flandri were the first to analyze that. And now taking account of random noises, the equation is formulated like this. And this is now in one-dimensional space. So D is 1, it's just on the interval. And then you look at this equation. So now this is just our noise, again additive noise. And now you can see we're in one dimension, so these are the derivatives, and now you even have in the linear part a fourth order operator. And then it's minus the second part, and this is the nonlinear part. And it turns out this equation has some features concerning irregularity which is close to the 3D Navier-Stokes if you go to 2 dimensions. Okay, so therefore there's an interest now to study this equation better, first in 1 dimension, and now in order to come to close, we take here H to be W22, V, V042, it's just in convenient spaces, then the V star, and then by our stochastic version of our existing theorem, so we have some condition on V as usual, but any initial condition now with values in W22 would exist a unique local solution with this property. So to compare with the result of Blomka and Flandely, they are mainly interested in this noise where it's a white noise, and this is not possible because B is in our case always a Hilbert-Schmidt value. This is due to the variational approach. So they are interested mainly in the white noise case. So that means that because of 1 dimension this is okay, because this is regularizing enough, and also some things can be done in 2 dimensions. But our techniques are just tailored for the non-white noise case. And what we want to do in the future is, of course, what you can always do is you can approximate the white noise by a noise that has a Hilbert-Schmidt operator in front, and then just develop a good machinery to use the variational approach for the approximations and then go to the limit. So then you don't have to I'm not saying that I don't like the semi-group approach, which you need in order to handle white noise, but I think it is just a limit of the variational approach in a sense. And by the way, the semi-group approach is not more general than the variational approach. It cannot, for instance, handle any better the Porous media equation, for instance. So the 2 approaches are in competition. There's an overlap, but one is not more general than the other. My feeling is that by approximation one can probably get all results from the mild solution approach by a variational approach. But this is only my philosophy. Nevertheless, I like the mild solution approach. Anyway, so then, as I said, we now up to some stopping time. So this is the stopping time. So we have a solution to this equation, and I think then maybe I'll finish a little early. And this afternoon I will tell you about extinction. Thank you very much.